All right, welcome everyone. Today we're going to do something pretty cool. We're going to build the entire real number system from scratch. Think of it like we're architects, and we're creating a visual blueprint for how all of math is built. We're going to see how every single number you can think of has its perfect place in this big, beautiful structure. Okay, so here's our game plan for today. First, we'll look at the big picture, the entire mathematical universe. Then we'll dive into what makes different numbers tick. After that, we'll get our hands dirty working with the infinite, and then tackle the power of exponents. And to wrap it all up, we'll look at the master blueprint that ties everything we've talked about together. Sound good? Let's get started. So, let's start with the whole universe of numbers. What you're seeing here is basically a map. The real numbers, that's everything. It's the whole container. And look how it's organized. You've got these nested boxes, right? The very first numbers we ever learn, the counting numbers, 1, 2, 3, those are the naturals. Add 0 to that and you get whole numbers. Throw in the negatives and now you have integers. And see how they all fit snugly inside this bigger box called rational numbers? But then, you've got this other group, the irrationals, kind of hanging out on their own. They're part of the real number universe for sure, but they play by a different set of rules. And that brings us to this, the Great Divide. This is the most fundamental split in the number world, rational versus irrational. It all comes down to one simple idea. A rational number, as you can see, can always be written as a fraction. That's its defining feature. And because of that, its decimal version will either stop, terminate, or it'll fall into a repeating pattern forever. Irrationals? Nope. You can't write them as a simple fraction, and that's why their decimals are just wild. They go on forever and ever with absolutely no repeating pattern. Okay, let's dig a little deeper into this. So you see a square root sign, and you might think, that's got to be irrational, right? Well, not so fast. It's kind of an illusion of perfection. Take a look here. The square root of a perfect square, like 4, is super clean. It just resolves into the number 2, which is totally rational. But if you take the square root of an imperfect square, like 5, it just shatters. It explodes into this endless, non-repeating decimal. That's the irrational part. Now, this is where things get really mind-bending. Look at the space between two whole numbers, say 3 and 4. You'd think there's not much going on in there, right? Wrong. There's actually an infinity of rational numbers packed in there. It's all about density. This infinite magnifying glass idea is a great way to see it. All we're doing is multiplying 3 and 4 by a clever form of 1, in this case, 7 over 7, and boom, suddenly you reveal this whole hidden grid of fractions, 22 sevenths, 23 sevenths, and so on, all living between 3 and 4. And you could do that forever with bigger and bigger numbers. So how do you even deal with a number that goes on forever? You can't write it down, you can't measure it with a ruler, but you can build it perfectly. And geometry is our toolkit. Check this out. We just build a simple right triangle where the two short sides are exactly 1 unit long. Thanks to our old friend, the Pythagorean theorem, we know with absolute certainty that the longest side, the hypotenuse, has a length of exactly the square root of 2. Then we just use a compass, like a bridge, to swing that length down onto our number line. And there it is. We've captured an infinite decimal and given it a perfect physical home. And the cool thing is, we don't have to stop there. This whole process is stackable. We can actually use one irrational number to build the next one. So we take that length we just made, the square root of 2, and we use it as the base of a brand new triangle. We add another side of length 1, run the Pythagorean theorem again, and what do we get for a new hypotenuse? You guessed it, the square root of 3. It's like building with mathematical Legos. And if you just keep doing this over and over, building a new triangle on the hypotenuse of the last one, you get this, the square root spiral. It's just gorgeous, isn't it? Each new hypotenuse gives you the square root of the next whole number, root 4, root 5, root 6, all spiraling outwards. It's this incredible visual proof that these seemingly chaotic, irrational numbers actually follow a predictable, beautiful geometric pattern. Okay, so building them is one thing, but what if you just see a number written out as a decimal? How can you tell what it is? Well, you can think of its decimal form as its decimal DNA. It tells you everything. This little chart breaks it down perfectly. You look at the decimal. Does it stop? If yes, it's rational. Does it go on forever, but in a repeating loop? Still rational. But if it goes on forever, with no pattern, no loop, just endless randomness, that's the telltale sign of an irrational number. Now, here is a fantastic shortcut, a real pro tip. How can you look at a fraction and just know if its decimal is going to terminate or repeat? without doing any tedious long division? You use this, the denominator diagnostic engine. It's super simple. You only need to look at the bottom number, the denominator. Break it down into its prime factors. And then you ask one question. Are the only prime factors 2s and 5s? If the answer is yes, that decimal will stop. Guaranteed. If there's any other prime factor in there, a 3, a 7, an 11, whatever, it's going to repeat forever. All right, let's switch gears and talk about working with these infinite beasts. How in the world do you trap an infinitely repeating decimal, like 0.6666, and force it back into a nice, neat fraction? It feels impossible, but it's actually a clever algebraic puzzle. Step 1, we give our problem a name. Let's call it x. So x equals 0.666. Then the key move is to shift the decimal point. Since only one digit is repeating, we multiply everything by 10. Now we have a new equation, 10x equals 6.666, with the decimal shifted one spot over. Okay, get ready, because this is the magic trick. It's called the shift and subtract maneuver. We take our new equation and stack it right on top of our original one. And look what happens. The infinite tails, all those repeating 6s, they line up perfectly. So when we subtract the bottom from the top, poof, the entire infinite part just cancels itself out. It vanishes. And we're left with this super simple equation, 9x equals 6. From there, it's easy. Solve for x, you get 6/9, which simplifies down to 2/3. We just trapped infinity. So what happens when these different types of numbers interact? What are the rules of engagement? Well, think of rational numbers as stable and predictable. But irrationals, they carry this unpredictability gene. And whenever a rational number mixes with an irrational one, that unpredictability is contagious. It infects the result. It doesn't matter if you add, subtract, multiply, or divide. A stable number plus an unpredictable one always gives you another unpredictable irrational number. But here's a crazy paradox. What happens when two irrationals meet? Well, all bets are off. It's completely unpredictable. Sometimes you multiply two irrationals, like √2 and √3, and you just get another irrational, √6. The chaos continues. But other times, two irrationals can collide and completely cancel out each other's weirdness. Look at √2 times √2. They combine and collapse into the perfectly stable, perfectly rational number 2. You just never know what you're going to get. Okay, when things get a bit more complicated, like this expression here, we need a system to make sure we don't miss anything. And that system is the good old distributive property. This diagram shows it beautifully. It's like a rule that says every part in the first set of parentheses has to shake hands with every part in the second set. So you follow the lines. The 3 multiplies with the 2, and the 3 multiplies with the √2. Then the √3 gets its turn, multiplying by the 2, and finally by the √2. It's a methodical way to make sure every connection is made. All right, here's an important rule of mathematical etiquette, or really structural engineering. Having an irrational number in the denominator, the bottom of a fraction, is a big no-no. It's like building a house on a shaky, unpredictable foundation. It's just not stable. So we have a technique to fix it called rationalizing the denominator. And we use this clever tool, the mirror multiplier. We multiply our fraction by a special form of 1, in this case, √3 over √3. It doesn't change the fraction's value at all, but look what it does. It transforms that shaky, irrational denominator into a solid, stable integer. Now our foundation is sound. Okay, time to add a seriously powerful tool to our toolkit. Exponents. This dashboard right here gives you the 4 core rules you absolutely need to know. They're the laws of how numbers grow and shrink. Rule 1, the product law. Multiplying same bases, just add the exponents. Rule 2, the quotient law. Dividing same bases, subtract the exponents. Rule 3, power of a power. Raising a power to another power, you multiply them. And finally, power of a product. Got a bunch of stuff in parentheses raised to a power? That power gets distributed to everything inside. That's it. 4 key laws. So you see a fraction up there in the exponent and it looks weird, right? Intimidating? Don't worry. It's just a root wearing a clever disguise. It's actually 2 instructions in one. The bottom number of the fraction, the denominator, that's the root you need to take. The top number, the numerator, that's just a regular old power. So for something like 32 to the 2/5, the 5 on the bottom says take the 5th root. The 5th root of 32 is 2. Then the 2 on top says square that answer. So 2 squared is 4. Simple as that. Okay, this is a super common trip up, so let's make this crystal clear. A negative exponent does not make the number negative. Not at all. Think of that little negative sign as a command. It's an action button. It's like a trap door that tells the base, hey you, move to the other side of the fraction bar.
So if it's in the numerator, it drops down to the denominator. And as soon as it moves, it pays a toll. It loses its negative sign and becomes a positive exponent. That's all it is, a command to move.
And here's a perfect example of how these rules all click together, like pieces of a puzzle. We're multiplying two things with the same base, which is 5. So right away, the product law kicks in. We just need to add the exponents. Now, who cares that the exponents are fractions? The rule is the rule. It still works. We just need to do a little fraction work. Find a common denominator for 2/3 and 1/5, add them up, and that gives us our final single exponent. It's elegant.
And that brings us here to the master blueprint. This is the grand finale. This one diagram pulls together every single thing we've talked about. You can see how that one big decision, are you rational or irrational, sets off a chain reaction. It determines what your decimal looks like, how you can be built with geometry, how you interact with other numbers, and how the laws of exponents govern you. It's all connected. Every concept, every rule is a critical structural element holding up this entire massive, beautiful mathematical universe. So there you have it. From the simplest numbers you count on your fingers all the way up to these complex exponent laws, it's not just a random collection of facts, it's one single interconnected system. And that really gets you thinking, doesn't it? If the abstract world of numbers is built on such an elegant and logical blueprint, what other blueprints are out there hiding in plain sight? What are the simple, elegant rules that create the complexity we see every day in music, in nature, or even in art?